So hello everyone, welcome to our video. We are group 32. I'm Yang Hanwen, and today we will explore the applications of differentiation and integration in solving engineering problems. First, problem 1 will focus on how differentiation helps us model a car speed and acceleration under air resistance. We will see how using differential equations provide a better understanding of how speed change over time, particularly as drag increases. Next, we will move to problem 2, where we calculate the volume of a hemispherical fuel tank using the method of value of revolution. This will show how calculate allows us to derive the value from the semicircle equation and apply it to real-world scenario. Through these two problems, we aim to demonstrate the practical importance of differentiation and integration in engineering. Now, let's dive into problem 1.
Hello, my name is Yuen, and I'll be explaining problem 1, which is about how differentiation is used to model the speed and acceleration of a car when air resistance is acting on it. In real life, a car cannot accelerate forever. Therefore, the car has to go faster, and the air pushes it back. And this force is called drag. To know how a car's speed actually changes over time, we must use differentiation, because differentiation tells us how fast something changes. Instead of just using simple formulas such as V equal U plus AT, we can use a differential equation to get more accurate results of a car or an object that is moving. So let's start with the equation for drag, which is F drag is equal to kv squared. So in this equation, V is the speed, and in this case, K is the coefficient of wind resistance, or the drag resistance. Next, we can use Newton's second law. The net force on the car is F net equal F engine minus F drag. Newton's second law states that F is equal to ma, which is equal to m dv by dt. By putting it all together, we get m dv by dt equal to F engine minus kv squared. This differential equation explains how the car's speed varies over time. It demonstrates that acceleration is not constant. It decreases as speed increases because drag gets stronger. To make it more relatable, think about when you're driving on the highway. But once you reach a speed like 100 km per hour, pressing the accelerator does almost nothing. Although the speed increases very slowly, you can hear the engine becoming louder. So low speed and drag is small and acceleration is high. At high speed, drag is strong and acceleration is very small. Differentiation also allows us to calculate these changes accurately at every instance. Okay, so now let's try with a real world example. Let's assume a mass of a car 1000 kg and the force on the engine is 3000 newtons, and that the drag constant is k is equal to 0.8. We can get the equation 1000 dv by dt equal 3000 minus 0.8 v squared. At first, v is equal to 0. And dv by dt is equal to 3 meter per second squared. The car accelerates to 60 meter per second. So dv by dt is equal to 0.12 meter per second squared. Now that drag is almost equal to the force of the engine, there is very little acceleration. This explains why vehicles have a top speed, which is the point where drag and engine force level out, making dv. So now dv by dt is equal to 0. So there's no more acceleration. And then here's a graph about it. So in this problem, we use differentiation to understand how a car speed changes. When air resistance is present, we can figure out how acceleration changes at various speeds, and why it decreases as the car accelerates by looking at the derivative of speed. Compared to assuming constant acceleration, this results in a more realistic model. This shows how differentiation helps engineers analyze moving objects in detail. It helps engineers analyze performance, develop engines, and improve aerodynamics by trying the calculus of rates of change to an actual vehicle's performance. Overall, differentiation turns a physical problem into a clear mathematical explanation.
Hello, my name is Enyu, and then I will be explaining problem 2. For this part, I choose to calculate the volume of hemispherical fuel tank using the methods of volumes of revolution. Fuel tank in real life can have many shapes, and then one of the common shape is hemisphere, which is like half of the sphere. To know that how much fuel can store, we have to calculate its volume. Instead of just memorizing the formula, we can use calculus to calculate the volume. This will also give us a deeper understanding of the math behind it. We start with the equation of semi-cycle, and our formula will be this. And then top half of the cycle is represented with radius of r, and then I will only look at the right x equal to 0 to x equal to r. Because when we rotate the part of the x-axis, it will be a complete hemisphere. When this semi-cycle region spins around the x-axis, the shape created is hemispherical fuel tanks. This is how we model the real-life tanks, using the simple equation, the rotation of 3D. To find the volume, we have to use this method. At any position x, we slice a very small piece of the area on revolving the slice around the axis. It is a thin disc. The radius of the disc is equal to the volume of y, and then the area of will be that formula. And then to get the whole volume, we integrate this formula, and then x equal to r, and x equal to 0 to x equal to r. And then this integral is the sum of the discs along the centers of hemisphere to the edge. In order to relate it to the real life, we should assume that the tanks have the radius of 1.2 meter. If we plug into the formula, and then we will get 3.6 cubic meters of fuel, which is a large amount of and useful of machines or storage system. So in summary, I used the semi-circular equation, applied this method, and then set up the integral and then solve it to find the volume of hemispherical fuel tank. This shows how calculus helps us to understand the calculate real world shape.
Hi, my name is Aaron. We have just taken a look at two examples that apply calculus in real-world contexts. Firstly, we saw that differentiation is needed for analyzing motion realistically. What does that mean? We learned that simple formulas fail when dealing with a complex reality like air resistance. Instead, we form a differential equation, and it does not just calculate a car's speed, but it also calculated how acceleration decreases as drag increases. This is how engineers design safer, more efficient vehicles which are safer for passenger use. Secondly, we demonstrated the usage of integration through the volume of revolution. Instead of just accepting the formula of a hemisphere, what we did is we derived it by using the disk method, which is slicing the shape into many thin components and adding them up. We calculated the precise capacity of a hemispherical fuel tank. Integration is essential for everything from designing storage containers to calculating the total work done by machines. Ultimately, calculus is not just abstract mathematics. It is the ultimate tool for turning physical problems into clear, solvable equations. Differentiation and integration provide the foundation for innovation, efficiency, and safety in the real world. Thank you very much.